Hello everyone and welcome to our channel Mootechie. It's a pleasure to have you here whether you're a seasoned craftsman, an aspiring student of the trade, or simply curious about the art of metalworking. Today, we're diving deep into the world of the smithy, exploring the fundamental tools and processes that transform raw metal into functional and beautiful objects. Get ready for an engaging journey into the heart of forging. Now let's begin by understanding the very basics. A smithy's work involves heating a metal stock to a desired temperature, enabling it to obtain sufficient plasticity, followed by operations like hammering, bending and pressing to give it the desired shape. This entire process is what we know as forging. These operations can be carried out in different ways, by hand hammering, by power hammers, or by forging machines. When it's done by hand tools, we call it hand forging. When it's done with the help of power hammers, it's known as power forging. If it's carried out by means of drop hammers, it's called drop forging, and when done by forging machines, it's referred to as machine forging. Moving forward, we'll see that applying pressure for shaping the metal always requires heating the metal to a definite temperature to bring it into a plastic state. This is the core principle. This heating may be done either in an open hearth, known as a smith's forge, or in a closed furnace. Small jobs are normally heated in the smith's forge, while larger jobs require closed furnaces. The hand forging process is employed for relatively small components, machine forging for medium-sized and large articles requiring very heavy blows, and drop forging for the mass production of identical parts. So the method chosen really depends on the scale and the specific requirements of the job. Next, we explore the principal tools and other equipment used in hand forging. This is the smith's toolkit. The key items are the smith's forge or hearth, the hammer, the swage block, chisels, punches, flatters, set hammers, fullers, and swages. Let's understand each of these in more detail, starting with the heart of the workshop. First, the smith's forge or hearth. It has a robust cast iron or steel structure consisting of 4 leg supports, an iron bottom known as the hearth, a hood at the top and a tuyere opening into the hearth either from the rear or from the bottom. Air under pressure is supplied by a blower placed near the forge through this tuyere opening. This blower can either be hand-operated or power-driven. Now let's look at the anvil. To carry out forging operations successfully, you need a proper supporting device capable of withstanding heavy blows. The anvil is the perfect choice for this. Its body is generally made of cast steel, wrought iron or mild steel, and is provided with a hardened top, about 20 to 25 mm thick. The diagram shows us the different parts of the anvil: the face, the handle hole, the punching hole, the tail and the body. The cutting face is a specific area used for chiseling. Coming up, we'll discuss the hammer. Sledge hammers are comparatively 3 to 4 times heavier than hand hammers. They are available in varying sizes and weights from 3 kg to 8 kg. They are employed when heavy blows are needed in forging and other operations done on heavy jobs. The image also shows a mallet, which is a type of wooden hammer, alongside the sledge hammers. Following this, let's understand the swage block. It is usually a block of cast steel or cast iron carrying a number of slots of different shapes and sizes along its 4 side faces and through holes from its top face to bottom face. This is used as a support in punching holes and forming different shapes. The job to be given a desired shape is kept on a similar shaped slot, which acts as a bottom swage, and then the top swage is applied on the other side of the job. The holes in the top and bottom face are used in punching. Their use is clever. It prevents the punch from spoiling by striking against a hard surface after the hole has been punched. Now let's talk about tongs. They are used to hold the jobs in position and turn them over during the forging operation. They are made of mild steel. Tongs are usually made in 2 pieces, riveted together to form a hinge. The smaller length on one side of the hinge carries the holding jaws, which are made in different shapes and sizes to suit the corresponding shapes and sizes of the jobs. The longer portions on the other side of the hinge form the arms, which are held in hand by the smith. The figure illustrates different jaw types: the square nose, the round nose, and the angle or VE nose. Tongs are usually named after the inside shapes of the jaws. Flat tongs are used for gripping thin sections and small flat pieces. Round hollow tongs with a curved surface inside are used for holding round work. Hollow tongs with square jaws are used to hold square or hexagonal work. And pickup tongs have their jaws so shaped that even small sections can be easily picked up, though they are not used for holding the work during forging itself. Let us now look at flatters. These are also known as smoothers. They are made of high carbon steel and consist of a square body fitted with a handle and a flat square bottom. They are used for leveling and finishing a flat surface after drawing out or any other forging operation. Think of them as the smith's smoothing iron. Next, the set hammer. It is used for finishing corners formed by two adjacent surfaces at right angles. The job is supported on the anvil and the tool is hammered from the top to create a sharp, clean corner. Now, on to fullers. These tools are made of high-carbon steel in different sizes to suit various types of jobs. They are usually used in pairs, consisting of a top and a bottom fuller. Their working edges are normally rounded. They are employed for making necks by reducing the cross-section of a job and are also used in the drawing out process. The diagram shows the top fuller and bottom fuller in action on a piece of work. And finally, in our tool overview, we have swages. Like fullers, they are also made of high-carbon steel in two parts called the top and bottom swages. Their working faces carry circular grooves to suit the size of the work, and they are available in various sizes. The top swage carries a handle, and the bottom swage has a square shank to fit the hardy hole of the anvil during the operation. They are used for increasing the length of a circular rod or for finishing the circular surface of a job after forging. Now that we know the tools, let's understand the materials they work with. What can we actually forge? The materials that possess the ability to sustain substantial plastic deformation without fracture, even in the presence of tensile stresses, can be forged easily. Common forgeable materials include wrought iron, low and medium carbon steels, low alloy steels, aluminium, magnesium, and copper alloys. Materials like austenite and martensite, stainless steels, and nickel alloys can be forged, but with some more difficulty. Forging materials must be heated to a temperature at which they will possess high plastic properties both at the beginning and at the end of the forging process. This is crucial. If the forging operation is finished at a lower temperature, it leads to cold hardening and cracks. On the other hand, with excessive heating, the forgings suffer from oxidization and much metal is wasted. The approximate temperatures for forging common metals presented in a table. Let's read it clearly. For wrought iron, the temperature at the beginning is just below 1300 degrees Celsius and at the end, it's 800 degrees. For low carbon steels, it's 1250 to 1300 degrees at the start and 800 to 850 at the end. For hard high carbon and alloy steels, it's 1100 to 1150 degrees at the beginning and 825 to 875 at the end. For brass and bronze, it's 950 degrees to start and 600 to finish. And for aluminium and magnesium alloys, it's 500 degrees at the beginning and 350 at the end. For hand forging, the temperature of heating steel can be estimated by the heat color. Let's look at this fascinating color guide. A faint red indicates about 500 degrees Celsius. Blood red is around 650 degrees. Cherry red is about 750 degrees. Bright red is 850 degrees. Salmon color is 900 degrees. Orange is 950 degrees. Yellow is 1050 degrees. And a white heat is around 1200 degrees Celsius. So, the smith learns to read the metals glow like a language. Now let's get into the action. What are the fundamental forging operations? They are 1. Upsetting, 2. Drawing out or drawing down, 3. Cutting, 4. Bending, 5. Punching and drifting, 6. And setting down and finishing. Let's explore each one. First, upsetting, also known as jumping. Upsetting is the process through which the cross-section of a metal piece is increased with a corresponding reduction in its length. You're basically making it shorter and fatter. The diagram illustrates this. An upper die moves down onto a billet which is resting on a lower die. After plastic deformation, the product is shorter and has a larger cross-section. Next, drawing out. This process is also known as drawing down. It is exactly the reverse process of upsetting. It is employed when a reduction in thickness, width, or both of a bar is desired with a corresponding increase in its length. You're making it longer and thinner. The image shows an undrawn bar being acted upon by a die to become a drawn bar. Now, for cutting. Cutting of metals in hot or cold state is done by means of hot or cold chisels respectively. The side view diagram shows a chisel being used to shear through a piece of metal. Let's move on to bending. Bending of bars, flats, and other similar stock material is usually done in a smithy shop. This can be done to produce different types of bent shapes, such as angles, ovals, and circles. The image depicts the bending process, showing a flat sheet being bent over a form with a hammer. Now let's understand punching and drifting. These are used for producing and finishing holes, preparing the metal for other shapes. Punching creates the initial hole. Drifting is the process by which a punched hole is enlarged and finished to the desired size and shape. The diagram shows a drift tool being driven through a hole in a piece of hot metal to enlarge it. And finally, setting down. It is a localized drawing down or swaging operation. Usually, the work is first fullered at the place where the setting down is to happen, and then the set hammer is used to finish it. The diagram shows the fullering operation with a top and bottom fuller on the work, and then the use of a flatter and a set hammer for flattening and setting down. As we continue, let's look at two broader forging methods. First, Smith die forging, also known as open die forging. The diagram, labeled Figure 4.4, shows an original shape of metal being pressed between two simple dies, die 1 and die 2, to achieve a final shape. The dies don't fully enclose the metal. And lastly, impression die forging, or closed die forging. Figure 4.8 shows a series of dies. The workpiece goes through multiple stages, a first stage, a second stage, and a final stage, where each die impression shapes the metal more precisely until it takes the final detailed form. This is how complex, identical parts are mass-produced. And that brings us to the end of our lesson on the smithy and forging tools. We've journeyed from the basic definition of forging, through all the essential tools like the anvil, hammers and tongs, understood the critical temperatures and explored the fundamental operations that shape metal. It's a beautiful blend of art, science, and sheer physical skill. Thank you for your attention and passion for learning. Keep that fire of curiosity burning. Thank you. See you in the next class.